The halogens form the seventh group in the periodic table, located just before the inert noble gases. The halogens are the most toxic and reactive of the non-metal elements. Each halogen has a distinctive color, getting darker as you move down the group. They are also poor conductors and have low melting and boiling points. Fluorine is a highly toxic pale yellow gas. It is the most electronegative and reactive of all the elements in the periodic table, and can even form compounds with the noble gases. Because of its immense reactivity, it is difficult to isolate and store in its pure form. Chlorine is a yellowish-green gas that combines with nearly all elements. We use chlorine's high water solubility to our advantage by adding it to drinking water to kill harmful bacteria. Bromine is the only non-metallic element that is a liquid at room temperature. It is isolated from seawater for industrial use. It is a brown, noxious, and heavy liquid that is highly corrosive to human flesh, causing sores when exposed to skin. Iodine is a shiny bluish-black solid. Heating iodine to just over room temperature causes it to spontaneously sublime, meaning that it changes directly from a solid into a gas. Iodine readily reacts with most elements in the periodic table, but it will be displaced from its compounds by any of the lighter and more reactive halogens. Astatine is the only radioactive element of the halogen group. The longest half-life recorded for this element is just over 8 hours. Astatine has a metallic appearance and is semi-metallic in nature. The halogens are typical nonmetals with relatively low melting and boiling points. The melting and boiling points increase steadily going down the group. Fluorine and chlorine are gases at room temperature. Bromine is a reddish-brown liquid, and iodine and astatine are solids. Halogens readily combine with hydrogen to form hydrogen halides. These covalent compounds quickly dissolve in water to form extremely strong acids. Hydrogen fluoride is used to strip solid gold from circuit boards. The human body uses the super strength of hydrochloric acid to break down anything in the stomach. Looking at the periodic table can help explain the reactivity of the halogens. Here, the elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In its normal, or ground state, this nucleus is also surrounded by an equal number of electrons. And as the atomic number increases, so does the size and mass of the atoms. In the periodic table, each horizontal line is called a period, and it represents the number of electron shells normally possessed by the element's atoms. For example, there are 4 electron shells in an atom of bromine, so it lies in period 4. Meanwhile, an atom of astatine in period 6 has 6 electron shells. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. Astatine, with an atomic number of 85, is the only radioactive element in the group. Halogen comes from the ancient Greek halo, meaning salt, and genes, meaning former. Minerals containing chlorine and bromine are found naturally in rock and sea salt. The halogens all have 7 valence electrons, so all the elements in the group have similar chemical properties. Almost all atoms need 8 electrons in their valence shell to be stable. Because they only need 1 more electron to have a complete valence shell, the halogens are extremely electronegative and very reactive. As you move down the group from fluorine to astatine, each element is less reactive than the one before it. This occurs because the attractive force of the positive nucleus becomes weaker as it is blocked by an increasing number of electron shells.
Element number 9 on the periodic table is fluorine. The atomic symbol for fluorine is F. Fluorine is a greenish-yellow, highly toxic gas that smells like bleach. Fluorine gets its name from the Latin word fluere, which means to flow. Fluorine is classified as a halogen. It lies in the periodic table's second row, period 2. Each atom of fluorine consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of fluorine, its nucleus has 9 positively charged protons, plus 10 uncharged neutrons. Fluorine has 9 negatively charged electrons to balance its 9 protons. These electrons are found in 2 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed among 1 orbital shell. Fluorine has 7 more electrons than helium. The first 2 electrons are found in the sphere-shaped 2s orbital shell. The final 5 electrons are distributed among 3 lobe-shaped 2p orbitals. Fluorine is the most reactive of all the elements, and it is never found uncombined in nature. Fluorine will always gain an electron when it interacts with other elements. In this experiment, a stream of pure fluorine gas is directed at a block of sulfur. Fluorine interacts with the sulfur to release energy in the form of heat and a bright light. The sulfur melts into a dark, thick, flowing liquid. The fluorine gas is then aimed at a cotton ball, which instantly bursts into flames. Fluorine compounds are added to water supplies and toothpaste to help prevent tooth decay. Other fluorine compounds are used to make light bulbs and lenses for focusing infrared light. Fluorine was also once widely used in air conditioning and refrigeration systems, before scientists discovered that it was damaging to the Earth's ozone. Parents get excited when they first start to come in, and kids get excited when they start to fall out. But one thing remains the same. Teeth are important to human health. You rely on your teeth when you chew food, when you talk, and when you flash your beautiful smile. Brushing, flossing, and regular visits to the dentist will help you care for your teeth properly and ensure good dental health. But other things can protect your teeth as well. One of them is fluoride, which is a compound of the element fluorine. Fluoride compounds occur naturally in rocks and soil, and calcium fluoride is found in all water sources. But fluoride is often chemically added to public drinking water. According to the American Dental Association, fluoride strengthens tooth enamel and reduces plaque's ability to produce acid. It also promotes the repair of tooth enamel that has already been damaged by acids. Topical fluoride is commonly applied to the surface of teeth in the forms of toothpastes, mouth rinses, and gels. They help protect the surface of teeth by making them more resistant to decay. Systemic fluoride comes from what you eat or drink, including the fluoride added to water and dietary supplements. Because the element fluorine has toxic properties that pose health risks, some scientists believe that fluoride should be applied to teeth directly and not be ingested. Some recent studies of systemic fluoride have sparked a debate over the value and safety of adding fluoride to public water supplies. But the one thing that all scientists can agree on is that the use of fluoride in toothpaste and mouth rinses helps strengthen tooth enamel, makes teeth healthier, and gives you a reason to smile and show off your pearly whites.
Element number 17 on the periodic table is chlorine. The atomic symbol for chlorine is Cl. A greenish-yellow, dense, sharp-smelling gas at room temperature, chlorine is extremely water-soluble and poisonous. Inhaling even a small amount of the gas could prove fatal. Chlorine comes from the Greek word chloros, which means greenish-yellow. Chlorine is classified as a halogen. It lies in the periodic table's third row, period 3. Each atom of chlorine consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of chlorine, its nucleus has 17 positively charged protons, plus 18 uncharged neutrons. Chlorine has 17 negatively charged electrons to balance its 17 protons. These electrons are found in 3 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed in 2 orbital shells. Chlorine has 7 more electrons than neon. The first 2 electrons are found in the sphere-shaped 3s orbital shell. The remaining 5 electrons are distributed among 3 lobe-shaped 3p orbitals. Chlorine is a highly reactive element, and the 7 valence electrons in this third-level shell influence how it interacts with other elements. A test tube is placed in liquid nitrogen. Chlorine gas is released from a pressurized cylinder into the test tube. As the chlorine gas comes into contact with the cold walls of the test tube, it quickly liquefies and then freezes. The test tube filled with solid chlorine is now removed from the nitrogen and placed over a glass bowl. The solid chlorine very rapidly melts and drips into the bowl where it undergoes sublimation, producing a faint yellow-green gas which disperses in the breeze. Chlorine's water solubility makes it very useful in treating drinking water in swimming pools. It is also commonly used as an antiseptic. Sodium chloride, more commonly known as table salt, can be found in every household. Hydrochloric acid is a strong and commercially important acid, as well as being necessary for food digestion. By the end of the 19th century, New York City was on the move. Waves of immigrants from all over the world were converging in Manhattan and reshaping the face of the city. Many of these immigrants were poor and faced harsh discrimination. They crowded together in tenements with horrific sanitation and hoped for a better life for their children. One of the terrors of slum life at this time was the outbreak of dread diseases such as typhoid and cholera. While people from all walks of life fell ill, these diseases particularly targeted the poor. It wasn't until the late 1800s that scientists finally determined that microorganisms known as bacteria caused both cholera and typhoid, and that these bacteria were spread in contaminated water. The discovery spurred a wave of improvements in city sanitation, including the introduction of treated drinking water. In 1908, Jersey City, New Jersey, just across the river from New York, was the first American city to sanitize its drinking water using chlorine. Chlorine is an ideal substance to kill microorganisms. It easily dissolves in water and does not dissipate, killing existent bacteria and preventing their regrowth. The advent of chlorinated drinking water, coupled with an overall improvement in sanitation practices, led to a drastic drop in the occurrence of waterborne diseases. By the 1930s, cholera and typhoid were virtually eliminated in areas with consistent water sanitation. Unfortunately, in many parts of the world, water still presents a danger. In underdeveloped countries in Latin America, Africa, and Asia, epidemics of cholera and typhoid still occur. Even in the United States, unprecedented disaster can threaten the water supply. Today, we know that just because water looks clean doesn't mean it's safe. Thanks to chlorine, we can make sure that the water from the faucet won't make us sick.
Element number 35 on the periodic table is bromine. The atomic symbol for bromine is Br. Bromine is a heavy red-brown liquid with a strong odor and is the only non-metallic element that is a liquid at room temperature. Bromine gets its name from the Greek word bromos, which means stench. Bromine is classified as a halogen. It lies in the periodic table's fourth row, period 4. Each bromine atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of bromine, its nucleus has 35 positively charged protons, plus 45 uncharged neutrons. Bromine has 35 negatively charged electrons to balance its 35 protons. These electrons are found in orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Bromine has 17 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The next 10 electrons fill 5 clover-shaped 3d orbitals. And the final 5 electrons are distributed among 3 lobe-shaped 4p orbitals. Since the electrons in the 3d orbital are at a lower energy state than those in the 4s and 4p orbitals, only the 7 valence electrons in this 4th level shell influence how bromine interacts with other elements. In this experiment, bromine is taken from a beaker and dripped onto a dish. At room temperature, it begins to evaporate, with a heavy reddish vapor rising from the dish. Notice that the demonstrator wears rubber gloves to avoid coming in direct contact with the bromine, which can cause burns to the skin and irritations to the throat and eyes. The bromine is then dripped onto a wooden surface and begins to slowly evaporate until it disappears. Bromine compounds are used in water purification and in creating fumigants and fire retardant materials. Silver bromide, a chemical used in photography, accounts for the largest use of bromine today. Fire has many moods, many disguises, and many ways to kill. Every fire department is all too familiar with the risks, and the team of firefighters works hard to prepare for their next call. In the past, a firefighter's arsenal consisted mainly of water and courage. Today, science is shedding new light on fire's beautiful but deadly dynamic, using technology and chemistry to add to the firefighter's arsenal. Human civilization owes its existence to fire. In its heat, we forge tools and power technology. Our constant companion, fire lives like a tamed beast in our homes, lulling us into a false sense of security. Given the chance, it reverts to its deadly ways. The many faces of fire are all born of 3 humble ingredients: heat, fuel, and oxygen. Take away any one of these, and the fire dies. Heat releases gases from the potential fuel source into the air. The liberated gases combine with oxygen and create a volatile chemical cocktail ready to ignite with a single spark. Once the fire is burning, particles of carbon light up as they release energy. This is what we see as flames. The key to firefighting is to neutralize the three basic ingredients of heat, oxygen, and fuel quickly and safely. It's all hands on deck as the first call of the day comes through. From the moment the alarm is received, the pressure is on to get to the site of the fire as quickly as possible. For firefighters, entering the hungry jaws of the beast is all in a day's work. Equipped with guts and determination, they have science and technology on their side. Brominated flame retardant, known as BFR, is the first line of defense. Brominated compounds help protect electronics, furniture, and a firefighter's protective clothes. Brominated flame retardants are incredibly effective at fire prevention.
3, 2, 1.
They reduce the combustibility of everyday items and hinder the spread of the fire to provide valuable time for escape. The bromine in BFRs disrupts the chain reaction that keeps fire burning, effectively extinguishing the flame. While materials protected with bromine may still suffer heat damage, it is the flame that is so important to the spread of fire. By interacting with vital flame components, the brominated flame retardants quench a fire's flames and stamp out its spread. Brominated flame retardants buy precious moments that could mean the difference between life and death.
Element number 53 on the periodic table is iodine. The atomic symbol for iodine is I. Iodine is a shiny purplish-black solid that is violet-colored in its gaseous state. Iodine gets its name from the Greek word ioides, which means violet-colored. Iodine is classified as a halogen. It lies in the periodic table's 5th row, period 5. Each atom of iodine consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of iodine, its nucleus has 53 positively charged protons, plus 74 uncharged neutrons. Iodine has 53 negatively charged electrons to balance its 53 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Iodine has 17 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The next 10 electrons fill 5 clover-shaped 4d orbitals. And the final 5 electrons are distributed among 3 lobe-shaped 5p orbitals. Only the 7 valence electrons in the 5th level s and p orbitals influence how iodine interacts with other elements. In this demonstration, a test tube full of solid non-metallic iodine pellets is placed in an electric coil. As the coil is heated, the solid pellets become a liquid, which quickly changes to a deep violet vapor. As the rising vapor cools, small glittering crystals of solid iodine can be seen forming in the smoke. Iodine is used to test for starch, turning a deep blue when it is present. Iodine compounds are used to make photographic film. Very small amounts of iodine are found in thyroxine, a hormone required by the thyroid gland to control the human body's rate of physical and mental development.
Element number 85 on the periodic table is astatine. The atomic symbol for astatine is At. Astatine is represented here by a sample of uranium ore, since it is always present in minute amounts with uranium. Because it has a very short half-life, astatine is named from the Greek astatos, meaning unstable. Astatine is classified as a halogen. It lies in the periodic table's 6th row, period 6. Each atom of astatine consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of astatine, its nucleus has 85 positively charged protons, plus 125 uncharged neutrons. Astatine has 85 negatively charged electrons to balance its 85 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Astatine has 31 more electrons than xenon. The first 2 electrons are found in the spherical 6s orbital shell. The following 14 electrons fill the 7 lobe-shaped 4f orbitals. The next 10 electrons fill the 5 clover-shaped 5d orbitals. And the final 5 electrons are distributed among the 3 lobe-shaped 6p orbitals. Only the 7 valence electrons in the 6th level s and p orbitals influence how astatine interacts with other elements. Astatine occurs naturally from the radioactive decay series of uranium and thorium, so it is radioactive as well. It is represented here by uranium ore. A Geiger counter measures the radiation it emits. Astatine is a rare short-lived element. Its half-life is only 8 hours. The element has no practical applications. It can be synthesized by bombarding bismuth with alpha particles. If it were possible to create enough astatine to see with the naked eye, the heat generated by its intense radioactivity would result in its complete evaporation, and its radiation would be fatal.